Today we are going to look at optimization examples. Optimization is the real-life applications of calculus where we want to maximize profit or minimize the material used, or whenever we want to maximize or minimize something, we would use optimization. Maximum minimums only occur when the derivative is equal to zero or derivative does not exist. And it can happen at the endpoints as well. So these are applications of calculus that allow us to determine the minimum or maximum value of a problem. For example, we're looking for greatest profit, or least time, or greatest voltage, or optimum size, greatest strength, or least distance. This is an application of absolute extrema and involves optimizing a function. This means finding the maximum or the minimum value of the function. To solve optimization problems, we would determine the function which we want to optimize, and then we would find the domain of the function. Then we would find the derivative of the function and set the derivative equal to zero, or find where the derivative does not exist. So either derivative is zero or derivative does not exist. So either derivative is zero or derivative does not exist. Those are the points where I can have maximum and minimums. Let's look at an example. Manufacturer wants to design an open box having a square base and surface area of 108 square inches. What dimensions will produce the box with the maximum volume? So we know the volume of the box would be x times h, because the volume of a box is length times width times height. So in this case, my base is square, so that's going to be x times x. So I would have x times the height. That would be the volume in this case, which is x squared times h. Surface area is given to me that we don't want the surface area to be no more than, want the surface area to be 108 square inches. So what's the maximum volume we can fit into a box whose surface area is 108 inches? So let's see, surface area 108 consists of 6 surfaces, the top, bottom, and the 4 sides. The top and the bottom are both going to be, so the bottom is going to be x squared, and oh, this is an open box, so we're not going to have 6 surfaces. We'll actually have only 5. So the bottom is x squared, and the 4 sides are going to be xh plus xh plus xh plus xh. This is the area of 4 sides. X squared plus 4xh is equal to 108. Now we know the volume is equal to x squared h. We want to maximize the volume. So here we have 2 variables on the right hand side. We want to express these variables in one variable in terms of the other. So let's go ahead and solve. From here, it's easy to solve for h. So I'm going to solve for h. H would be 108 minus x squared over x. 108 minus x squared over 4x actually. That's going to be h. Now let's think about the domain in this case. So we want the x to be greater than 0. We also want the h to be greater than 0. That means 108 minus x squared over 4x has to be greater than 0. 108 minus x squared has to be greater than 0. Or we can say x has to be, if I take x squared on the other side, 108 is greater than x squared, or x is less than square root of 108. I'm not going to consider positive and negative because it's the length, and the length is always positive. So x is less than square root of 108. Okay, so I got the h. Now I'm going to plug this in here because that's the function we want to maximize. So let's find the volume. So we know the volume is x squared times h. So instead of h, I'm going to write 108 minus x squared over x. This leaves me with v equals 108x, because we can cancel one of the x's here, minus 108x minus x to the third. 108x minus x to the third. And we did have over 4. There was a 4 over here as well. So it stays with both of them. Now we do have the right hand side in one variable. I'm going to go ahead and do the derivative, find the v prime, and then set that derivative equal to 0. So v prime would be the derivative. That's going to be 108 over 4 minus 3x squared over 4. 108 over 4 minus 3x squared over 4. Now to find the maximum or minimum, set v prime is equal to 0. So I'm going to set the derivative equal to 0 now. Let's set the derivative v prime is equal to 0. Set v prime is equal to 0, which is 108 over 4 minus 3x squared over 4 is equal to 0. So that's going to be 108 is equal to 3x squared, and I get x is equal to square root of 108 over 3. So that's going to be that's going to be the x. So the side of the square bottom would be x. So we would have the derivative is going to be, the volume is going to be maximum when x is equal to square root of 108 over 3. Now this is the only place where I have a max or min. Now if you really want to verify your max, you can go ahead and pick two x values around it and then find the volume after you find the h as well. So if x is 108, h, we earlier found a relationship between x and h. H was equal to 108 minus x squared over 4x. So that's going to be 108 minus x is 108 over 3 over 4 times square root of 108 over 3. So do these calculations using the calculator. We do have a value of x and h that will give me the maximum volume. Again, if you want to check if this is your maximum, you can go ahead and find the values around this and then go for check your volume. Pick the x values around this point. Pick one value on the left, one on the right, and then find the volume. Another example, a piece of wire of length L is bent into the shape of a rectangle. Which dimensions produce the maximum area? So we want to get the maximum area for this rectangle, and we're told that the length is L. Now we don't know what's going to be the width, what's going to be the length of the rectangle. The wire is length L, we know that. Wire is length L. So if I bend the wire, let's just say the length is x. If the length is x, then the x plus width has to equal L. So we can say 2x plus 2w equals L. 2w equals L minus 2x. Width would be L minus 2x over 2. So width turns out to be L minus 2x over 2. Okay. Now we want to find the maximum area. So let's find the area function. Area is going to be length times the width. Length is x and the width is L minus 2x over 2. Okay, now we're going to find the derivative. Before we do that, let's go ahead and clean it up a little. We can distribute. This would be Lx over 2 minus 2x squared over 2, which is going to be just x squared. Okay, now we're going to go ahead and find the derivative here, a prime, and set that derivative equal to 0. Set a prime is equal to 0. So the derivative in this case would be a prime turns out to be L over 2 minus 2x. Now we will set a prime is equal to 0. So L over 2 minus 2x equal to 0. L over 2 equals 2x. We can say x is equal to L over 4. So I'm going to have the maximum area when the length is L over 4. Length is 1/4 L over 4. Okay, the length is L over 4. All right, so if the length is L over 4, what's going to be the width? The width, we said this is L minus 2x over 2. So L minus 2 times L over 4 over 2, which is going to be L minus, this is an L. So L minus L halves over 2. So it turns out to be L minus L halves over 2, which is 2L minus L is L over 4 again. So it's going to be a square with the side L over 4. Square with the side L over 4. Okay, that's going to give us the maximum area if the length of the wire is L. Next example, find the minimum area. A rectangle page is to contain 24 square inches of print. The margin at the top and bottom of the page to be 1.5 inches and margin on the left and right be 1 inch. What should be the dimensions of the page so that the least amount of paper is used? Okay, so let's go ahead and think about, we want to have some paper where we have the side X and the side Y. And we want to have 24, we want the 24 inches is what the written print has to be in there. And then we have 1.5 on top and bottom and 1 on left and right. So 1.5 on top and bottom we have, and 1 on the left and right is going to be our margin. And we want to find out the dimensions so that the least amount of paper is used. least amount of paper is used. So least amount of paper will be used when the A prime is equal to 0. What's going to be the area of the whole page, not just the printed? We know 24 square inches in the middle, that's printed. But how about what's the total? The total is going to be x plus 2, because we have 1 added on each side, times y plus 3. Half on the top, half on the bottom. Now we do know that x times y is equal to 24. So if you look at without the margin in the written area, xy is equal to 24. We can either express x in terms of y or y in terms of x. So we can go ahead and say x is equal to 24 over y. In this case, x is equal to 24 over y. Let's say it doesn't matter which variable do you express in terms of the other, either x in terms of y or y in terms of x. 24 over y is what I'm calling the x. So 24 over y plus 2 times y plus 3. Let's go ahead and distribute. That would give me 24 over y times y would be just 24. 24 over y plus times 3, that would be 72 over y plus 2y plus 6. So A turns out to be 24 plus 6, which is 30. 24 plus 6 is 30. Plus 72 y to the power negative 1 plus 2y. Now find the derivative and set it equal to 0. The A prime is going to be derivative of 30 will be just 0. Negative 72 y to the negative 2 power plus 2. Now to find the max and min, we are going to set this derivative equal to 0. So negative 72 over y square plus 2 equal to 0. Negative 72 over y square equals negative 2. 72 over y square equals 2. 72 over 2 is equal to y square. Gives me y is equal to 6. So I can see the width of my paper is going to be 6. The y is going to be 6. So y is equal to 6. If y is 6, we can plug this in here and find out x is equal to 24 over 6, which turns out to be 4. So dimensions of the paper should be 6 times 9. 6 times 9 is what we should use to have, to have 24 square inches of print inside. And that's going to be inches, 6 times 9 inches. 6 inches times 9 inches. A farmer has 100 yards of fencing to form 2 rectangular pens and a third pen that is twice as long as the other 2 pens. All 3 pens have the same width x. Which value of the y produces the maximum total fence? So I think this is x and this is x. The width is same for all of these. Okay, so let's see. What are we going to do here? So first of all, I want to find the maximum total area. So the area is what we want to find out. Area is going to be xy, which is the area for this piece. Area for this piece will be xy. Area for this piece also will be xy. And area for this piece would be x times 2y. So xy plus xy plus 2xy, or x times 2y, which is 2xy plus 2xy, and that's a 4xy. Area turns out to be 4xy. Area turns out to be 4xy. Now we are told that there's 100 yards of fencing he has. He has 100 yards of fencing. So that means my perimeter is 100. So perimeter is 100 here, which is going to be, so perimeter in this case would be, I'm going to be fencing. So this is all the fence I have. That's 2y. That's another 2y. So 2y plus 2y. And then we have x, another x, 2 x's, third x, fourth x, fifth x, sixth, and seventh. Oh no, sorry. 2y is here, 2y is here, and 2y is on the bottom, another 2y. So I have 3 of the 2y's, because y plus y, y plus y, y plus y. And then we have x plus x, which is 2x, another x plus x, which is 4x, and then 1x in the middle, which is going to be 5x. So perimeter is given to me. It is 6y plus 5x is equal to 100. 6y plus 5x is equal to 100. Now we can either express x in terms of y or y in terms of x. So I can say from here x is equal to 100 minus 6 100 minus 6y over 5. 100 minus 6y over 5 is going to equal to x. Now, if you want to think about the domain here, we want x to be greater than 0. We also want the y to be greater than 0. So if we consider y greater than 0, we also want 100 minus 6y over 5 to be greater than 0. 100 minus 6y to be greater than 0. 100 is greater than 6y, or y is smaller than 100 over 6. That's my domain here. And we cannot have y equal to 100 over 6. We cannot have y equal to 0. It's going to be an open domain, open endpoints here for the domain, because if we have y equal to 0 or y, this is actually x. So if we have the closed interval here, then the y can equal 100 over 6 or y can equal 0. That means there's no area. We might just have one dimension in that case. So it's not equal to, it cannot equal endpoints. So here we're given a is equal to 4xy. That is the function we do want to maximize or minimize the total fenced area, which is 4xy, but we don't want to deal with the two different variables on the right hand side. So using the given information, we're going to express one variable in terms of the other, which we just did. We expressed x in terms of y. So now I can say the area A is equal to 4 times x is 100 minus 6y over 5 times a y, which turns out to be, let's go ahead and distribute. That's going to be 400 y over 5 minus 4 times 6 is 24 y over 5. Y squared over 5. All right, now to find the max and min, to optimize the function, we're going to optimize the function. We are going to set y prime or a prime is equal to 0. Okay, so to optimize the function, a prime is equal to 0. A prime is going to be, so find the a prime. A prime in this case would be 400 over 5, which is going to be 405 is 80, minus 24 over 5 times 2y, which is a prime, turns out to be 80 minus 48 over 5y. Now we're going to set this equal to 0 and solve it. So set the a prime is equal to 0 and solve for the x in this case, or solve for the y in this case, solve for the variable. So when I set a prime is equal to 0, 80 minus 48y over 5 is equal to 0. 48y over 5 is equal to 80. Y is equal to 80 times 5 over 48. Okay. Y is equal to 80 times 5 over 48. So we can go ahead and simplify here and use a calculator. See what does that turn out to be. 80 times 5 times 5. I'm going to go add a parentheses here and divide it by 48. That leaves me with 8.33 is my y value. 8.33. 8.33 is my y value. Now, if you really want to check that this is your max or min, like we talked about earlier, we can go ahead and make a table. This is 8.33 for the y value, and we said the y value has to be less than, we earlier found the domain, and we said it has to be 100 over 6. I believe it was less than 100 over 6. So you can check what's going to happen to your the derivative. If you plug, the derivative is going to be positive. That means your function is increasing. Derivative will be negative over here. If you pick a y value from here, that means your function is decreasing. So do you have a max at 8.33? That's just if you want to verify. If you end up with more than one critical point, then it would be necessary to check where do you have the max and where do you have the min. Okay, and so far all the examples, I've been getting only one critical point, so I'm not really checking if that's my max or min. I'm just assuming that if there's only one, that is going to be my max. But it's good to check around, picking the points around the max or min, around the x value, to see if that really is your max. So if y is 8.33, we also want to find out the x. I'm going to plug that back in here. X will be 100 minus 6 times 8.33 over 5. 100 minus 6 times 8.33 divided by 5. that is going to be 10.004. So 10.004, and in this case both are going to be yards, so y is in terms of yards and x is also in terms of yards. That's going to be the dimensions that I can have the maximum area using this much fence. Maximum area using this much fence. The rectangular bird sanctuary with one side open along the river is to be constructed so that it contains 8 kilometer square area. Find the dimensions of rectangle to minimize the area of fence, amount of fence necessary to enclose the remaining 3 sides. Okay, so we do have a river on one side and we want to enclose some area. Now I'm just going to say let this side be x and this side would be y. This side would be y. We want the area to be equal to 8. Okay. And we want to use the least amount of fence. So we want to minimize the perimeter of the fence in this case. The area is 8. That means x times y is 8. The perimeter is what we want to minimize. We want to minimize the amount of fence or the length of fence we do use, which is going to be x plus y, which is going to be x plus 2y. So this is the function that I want to minimize or maximize. It's very important to realize which function you want to maximize or minimize. In this case, I want to minimize this function. I want to find the smallest amount of fence, smallest length of fence that I need. Small perimeter, okay? So p is equal to x plus 2y. Now we don't want to deal with the two variables. We want to express one in terms of the other. We can either express x in terms of y or y in terms of x. So I can go ahead and say y is equal to, from here, y is equal to 8 over x. So area, or actually perimeter, p is equal to x plus 2 times 8 over x, which is x plus 16 over x. Perimeter is equal to x plus 16 over x. Okay, so now we're going to find the derivative and put it equal to 0 because we want to find we want to minimize this function. So set p prime is equal to 0. P prime is going to be 1 minus 16x to the power negative 2. 1 minus 16x to the power negative 2. So 1 minus 16x to the power negative 2 is 0, which I can write it as 1 minus 16 over x squared. 1 minus 16 over x squared is 0. 1 is equal to 16 over x squared. From here, x squared equals 16. X turns out to be 4. I'm not considering negative 4 because it's the length and the length is never negative. And right at this point, I should have also thought about the domain, which is very, very helpful. So we want our x to be greater than 0 and the y to be greater than 0, which means we want 8 over x to be also greater than 0. So 8, our x will be less than 8. My domain is going to be from 0 to 8. The x value has to lie from 0 to 8. It cannot equal 0. It cannot equal 8. I'm working with the open interval because if x is equal to 0 or x is equal to 8, I don't have two dimensions possible for the area. I will have just either x or y only. Okay, so x is equal to 4 is what we are left with. That's going to be our dimension. X equals 4. If x is 4, what is y going to equal? We can use this relationship. 8 over 4 is equal to 2. And it's going to be kilometers. That's all for this problem. Let's check out another one. Find two positive real numbers such that they add up to 108 and the product of first times the square of second is max. Okay. So we want to find the two positive real numbers. I'm just going to call them x and y. X and y. Those are my two numbers, x and y. They add to 108. So x plus y is equal to 108. Now let's talk about which function do we want to maximize or minimize. We want to, the product of first times the square of second is max. So we want to maximize the product of first times the square of second. This is the function we want to maximize, because it says we want the product to be max. So max and min only occur when the derivative is 0. I don't want to deal with the function in two variables, so I'm going to either express x in terms of y or y in terms of x. So we can go ahead and say x is equal to 108 minus y. So we want x to be greater than 0, which means we want 108 minus y to be greater than 0. 108 is greater than y, or y would be less than 108. So we want both y and x to be greater than 0. So my domain would be between 0 to 108. And the number cannot equal 0, it cannot equal 108, because if it is, then the other number will be 0. I wouldn't have two numbers. That was one thing that I was told, that there's two numbers. Okay, so let's express this function in terms of y only. Instead of x, I'm going to write 108 minus y times y squared. This leaves me with p is equal to 108 y squared minus y to the third. Now we're going to go ahead and to maximize this function, to maximize the function, which is called optimization, maximizing or minimizing. To maximize the function, set the derivative p prime is equal to 0. So p is 108 y squared minus y to the third. P prime is equal to 108 times 2 is 216 y minus 3y squared. 216y minus 3y squared. So p prime is equal to 0. That means 216y minus 3y squared is equal to 0. I'm able to pull out a 3y from here. 3y times 3 times 7 is 21. 72 minus y is equal to 0. So either 3y is equal to 0 or 72 minus y is equal to 0. Y is equal to 0 is not an option. We earlier talked about if y is 0, then we don't have the other number. We don't really have two numbers. So y is equal to 72 is my choice. So if y is 72, the x is going to be, I'm going to plug 72 in here for the y value which is found. So x would be 108 minus 72, which is going to be 72 and 36. That's going to be my answer. Now if you want to check this is your max or min, go ahead and draw the chart where your y value, we found the critical point was 72, and now pick a value closer to 72 and see what happens to this function, to the left side of 72, and see what is happening to the product here when you pick a value to the left and you pick a value to the right. What's happening to this product? You will see that it's going to give you the positive. Actually, plug it into the derivative to see if you have the derivative is positive or negative. Plug it into the derivative to see if your derivative is positive or negative. And then see, this is going to tell you that you have a max at 72. Okay. Another example, we have find two positive real numbers, x and y, such that they add up to 120 and x squared y is as large as possible. So x plus y add up to 120, very similar to the problem we just did. X squared y is large as possible. We want to maximize this function. We want to express one in terms of the other. So I can say y from here, I can say y is equal to 120 minus x. P is equal to x squared times 120 minus x. P is equal to 120 x squared minus x to the third. To maximize, we will set the derivative equal to 0. So to maximize, set p prime is equal to 0. So p prime would be 120 times 2 will be 240x, 240x minus 3x squared. 240x minus 3x squared is equal to 0. 240x is equal to 3x squared. And actually I don't want to cancel. I mean, in this case, it wouldn't matter if I cancel the x's. Normally, we would not cancel the x's because you lose one solution. I'm just going to factor out a 3x from here. 3 times 80 minus x. So either x equals 0 or x equals 80. We know x cannot equal to 0. We could talk about the domain in the beginning. We want x to be greater than 0, y to be greater than 0. 120 minus x to be greater than 0 as well. 120 is greater than x, or x lies between 0 and 120. So x cannot equal to 0, but I did get the solution x is equal to 80. So when x is 80, and y would be 120 minus 80, which is 40. These are the two numbers whose product x squared y will be maximum. Box has a square base and the surface area of 20. Find the dimensions to get the maximum volume. Sometimes they give you a problem where you have a piece of cardboard, you want to cut the ends to find the maximum volume. In that case, we would, again, the same strategy, we would think about use the given information to express the function that you want to maximize or minimize in terms of one variable only, and then go ahead and find the derivative and set the derivative equal to 0. In this case, I'm given the surface area is 20 and we want to maximize the volume, and I'm told that the box has a square base, so x squared times h is my volume. And the surface area, this is not the open top. So surface area is going to be x squared plus x squared plus 4xh, the top, the bottom, and 4 sides. And we're told that the surface area is equal to 20. So this is the function I want to maximize or minimize. I don't want to have two variables on the right hand side. I want to use one variable only. So I'm going to express either x in terms of y, or y in terms of x in terms of h, or h in terms of x. In this case, it's really easy. Actually, first of all, I'm going to go ahead and divide everything with a 2. Gives me 10 equals x squared plus 2xh. 10 minus x squared is equal to 2xh. 10 minus x squared over 2x is equal to h. So I'm going to plug that h in here. Volume comes out to be x squared times 10 minus x squared over 2x. Now let's go ahead and simplify here. I can cancel one of the x's. So volume turns out to be 10x minus x to the third over 2, which is 5x minus x to the third over 2 if I write as two separate fractions. Now to find the max or min, we're going to have to set the volume equal to 0. Before we proceed further, let's go ahead and think about, we want the x to be greater than 0 and we want the h to be greater than 0. That means we want 10 minus x squared over 2x to be greater than 0. 10 minus x squared to be greater than 0. X squared will be less than 10 if I add both sides. So x will be less than square root of 10 when I take square root on both sides. So between 0 to square root of 10 is my domain in this case. And again, I'm working with the open interval. I cannot have x equal to the endpoints because then I wouldn't be able to have a box. So set the derivative equal to 0. V prime is going to be 5 minus 3x squared over 2. Yep, equal to 0. So 5 is equal to 3x squared over 2, which is 10 is equal to 3x squared. X squared is equal to 10 over 3. X is equal to square root of 10 over 3. Now, I might want to rationalize, but hey, I'm just going to give a decimal answer. Okay. I'm going to give a decimal answer. So I would say x equals square root of 10 over 3. Whatever decimal approximation that is, that's going to be square root of 10 over 3. Approximately 1.82. And double check that this is going to be your maximum by making a chart. And this is 1.82, this is 0, this is square root of 10. And find the values of x around it. Pick a value to the left of, let's pick x equals 1 and see what happens to your derivative. When we pick x equals 1, my derivative would be 5 minus 3 halves. It's going to be positive. If you pick x as 2, my derivative will be negative. I can see there is going to be a max at this point. So that's my dimensions. X equals 1.82. Once you know the x, you also know the h. You can go ahead and plug the back into the h. And in this case, we're not given the unit, so it would be just whatever units. We can just say units next to it. So find out the h as well by plugging the x back into the relationship between x and h that we had. I'll leave that part for you. Next example, find the maximum area of a rectangle inscribed in a right triangle with the legs of the length 3 and 4 inches. The side of the rectangles are parallel to the legs of the triangle. So let's go ahead and draw the right triangle. And then we do have a rectangle inside. Okay, so we are given that the length of the legs of the triangle, one leg is 4 and the other leg is 3. We don't really know the sides of the rectangle inside, so I can just say the rectangle has the length x and the width y. Okay, maximum area of rectangle inscribed in a right triangle with the legs of the length 3 and 4. Sides of rectangle are parallel. So find the dimensions. So we want to find the dimensions for maximum area of rectangle. So we want to find the dimensions x and y that would make the area maximum. And if you want to find the area, then we can find the area as well once we know x and y. So I'm going to look for x and y. We want to maximize a is equal to x and y. This is my function that I want to optimize or maximize. Now, I'm not able to do the derivative and set it equal to 0, solve for one of the variables until I'm down to one single variable on the right hand side. So I'm going to go ahead and use a similar triangle relationship. I'm going to be using the similar triangle. I'm going to be using this triangle and the large triangle. So I have two triangles, the smaller triangle and the larger triangle. So side of the smaller triangle, x, over the side of larger triangle, 4. So x over 4 is equal to side of the smaller triangle, this side of the smaller triangle, which is going to be, so if this is y, that would be 3 minus y. This piece would be 3 minus y if the entire thing is y. Entire thing is 3 and a piece of it is y. So that would be 3 minus y over the side of larger triangle over 3. We can say x is equal to 3 minus y over 3 times 4. So we were able to find x in terms of y over x over 4 is equal to times 4. Yep. So now we want to go back to the area function and express x in terms of y. So x is equal to 3 minus y over 3 times 4 times a y. So that is, if I distribute, 3 over 3 is 1. So 4y minus 4 over 3y squared. That's the area. We want to maximize the area. We want to set a prime equal to 0. A prime is equal to 0. A prime is going to be 4 minus 4 over 3 times 2y. So a prime is equal to 0 gives 4 minus 4 over 3 times 2y is equal to 0. 4 over 3, that's going to be, if I solve for y, that would be negative 8 over 3y is equal to negative 4, which is going to be 8 over 3y is equal to 4, y is equal to 12 over 8. That's going to be 3 over 2. Y is equal to 3 halves is what I get. So y is equal to 3 halves. When y is 3 halves, if I plug that back in here, y is 3 halves. Let's see what does x come out to be. X would be 3 minus 3 halves over 3 times 4. 3 minus 3 halves is 1 and a half. That's 6 minus 3. That's again 3 halves, which is going to be 3 over 6 times 4. That turns out to be 2. So x is equal to 2. So my dimensions are 2 and 3 halves. X is equal to 2 and y is equal to 3 halves. These are the dimensions that will give me the maximum. X is equal to 2, y is equal to 3 halves is the dimensions that will give me the maximum area in this case. See another example. A 4-wheel vehicle is transporting an injured hiker to the hospital from a point that's 30 kilometers from the nearest point on the straight road. Okay, so somebody is injured. So this is where the hospital is. I'm going to find where should he hit the road. The hospital is 50 kilometers down the road from the nearest point. So from the nearest point, the total distance here is 50. The hospital is 50 kilometers if he goes directly in the right angle, at the right angle. If the vehicle can drive 30 kilometers per hour over the terrain and 1 kilometers per hour on the road, how far down the road should the vehicle aim to reach to minimize the time it takes to the hospital? So let's just say that we know distance is equal to rate into time. So we want to find out where should he hit the road? We don't really know. Let's just say he should hit the road after the distance x. So this is the x distance. We don't know. X distance past the nearest point on the road. Okay, so x distance past the nearest point on the road. We know distance is equal to rate into time. So we want to maximize the time. We want to find the time it takes the person. So we need to find the two kinds of times. One, the time it takes to get to this point. The second, the time it takes to go from here to here. Distance is equal to rate into time. That's not correct. Distance is equal to rate into time. So we can say time is equal to distance over rate. So the time on the terrain would be the distance covered on the terrain divided by the rate. And it's also given me that this is 30 here. So if this distance is, if one leg is 30, the other leg is x, the hypotenuse would be square root of 30 squared plus x squared. That would be the hypotenuse. That would be the distance the terrain area. So time would be distance, time would be the distance over the rate. The distance is square root of 30 square plus x square, and the rate at which they can go on the terrain is 30, yep, 30 kilometers per hour. And the time it would take on the straight road once they hit the point, whatever x distance is on the road, straight road, the distance they will have to cover is 50 minus x, and the time it would, the speed he can go on is 120. Okay, so we want to minimize this time. We want to minimize this time, right? We want to minimize the time. So to minimize the time, we want to set t prime is equal to 0. So let's go ahead and find the derivative t prime and set it equal to 0. So in this case, that would be 1 over 30. We'll have to use a chain rule. 1 over square root of 900 plus x squared times 2x plus 50 over 120, derivative for that piece will be 0, minus 1 over 120. That's what I would have, minus 1 over 120, because once I do the derivative, the x will be gone. T prime, this is the derivative, 1 over 30. We can also do this, 1 over 15, or x over 15. Let me call this x here. X over 15 square root of 900 plus x squared minus 1 over 120. So that's my derivative here. Let's go ahead and set the derivative equal to 0. When I do, there's going to be a 1/2 here as well. There's going to be a half here because when I do, there's the exponent 1/2. The exponent will come in the front. So I would have a 30 over here. The 2 and 2 will cancel. I will have a 30 here. It's going to be 30. I'll have a 1/2 here too when I do the derivative. Okay, so now we're going to set this equal to 0. Set t prime equal to 0. X over 30 square root of 900 plus x squared minus 1 over 120 equal to 0. X over 30. Now both these times are greater than 0. We could go ahead and think about the domain here. We could go ahead and think about the domain. Both of these times are going to be greater than 0. Let's go ahead and solve it for x. X over 30 square root of 900 plus x squared equals 1 over 120. Now I can make my life simple by doing this. X over square root of 900 plus x squared equals 1 over 4, which turns out to be 4x equals square root of 900 plus x squared. So 16x squared is equal to 900 plus x squared. 16x squared minus x squared is 15x squared. 15x squared is equal to 900. X squared is 900 over 15. X squared turns out to be 900 over 15. X would be square root of 900 over 15. I'm not considering the negative answer because time can never be negative. So square root of 900 over 15, that is 2 root 15, which is 7.75. So x is approximately 7.75. 7.75. So that's what I got, that they should hit the road after 7.75 kilometers. So this distance is 7.75 kilometers. They shouldn't hit the road directly here. They should hit it at the 7.75 kilometers further on the road. So that would give us the minimum time, and that would help us save the patient. So if you were to go ahead and think about if you get a max or min here, so the x distance we are talking about can be between 0 and 50. They could either hit the distance all the way at the closest point, which is x equals 0, or they could hit directly through the terrain at x equals 50, so between 0 to 50, and we got 7.75. Go ahead and plug this into the derivative. Go ahead and plug x as 1 in the derivative. You will get a negative answer. Your derivative will be negative. If you plug x as 10, derivative will be positive. That tells me I do have a min at this point. Okay, find the point on y is equal to x squared closest to the point 30. So for these kind of problems, wherever you're trying to minimize the distance, it's always nice and easy to minimize the square of the distance. So y is equal to x squared is given to me, and this is the point x and y. X and y. The distance formula, if you recall, is distance formula is going to be x2 minus x1 squared plus y2 minus y1 squared. x2 minus x1 squared plus y2 minus y1 squared is the distance formula. Now, let's say the point xy is closest to the point 3, 0. The point xy is closest to point 3, 0 on the parabola. The point xy on the parabola is closest. So this point is on the parabola. So we want to find the distance between these 2 points. That would be x minus 3 squared plus x minus 3 squared plus y minus 0 squared. So instead of minimizing the distance, we will minimize the d square. Same, it's going to give us the same results, but it's going to be easier to deal with. So we'll minimize the distance square. Minimize d squared, not just the distance. So d squared is x minus 3 squared plus y squared. We want to minimize the d squared. So d squared, first of all, we want to express y in terms of x or x in terms of y. We already have a relationship y is equal to x squared. So I'm going to replace that in the d squared. That would be x minus plus y is equal to x squared. That would be x to the 4th. Find the derivative of this square of the distance. You can just call it function p, k, l, m, whatever you want. It doesn't really matter. The derivative is going to be 2 times x minus 3 times 1 plus 4x to the 3rd. Now we want to set the derivative equal to 0. Square of the distance. Derivative of square of the distance. So set d square prime equal to 0. 2 times x minus 3 plus 4x to the 3rd is equal to 0. 2x minus 6 plus 4x to the 3rd is equal to 0. So how do we solve this function here? 4x to the 3rd plus 2x minus 6. Let's see. Just rewriting it. 4x to the 3rd plus 2x minus 6 equal to 0. Now it's a cubic equation. One thing I can see, if I have a square here, I'm just going to rewrite it. If I write it as 4x to the 3rd plus 0x squared plus 2x minus 6 equal to 0, I will probably have to use synthetic division and the rational zero theorem. But I can see that 4 plus 2 is equal to 6 and 0 and negative 6. So they add up to opposite. The alternate terms add up to opposite. That means x minus 1 is going to be a factor. 1 is going to be a 0 in this case. If I replace x by 1, I'm going to get a 0. 1 is a 0. And we can verify that. We can verify that 1 is a 0 by doing synthetic division. 4, 0, 2, negative 6. If I do synthetic division with the 1, I would have 4 times 1 is 4. 4 times 1 is 4. 6 times 1 is 6, which is going to give you 0. So we would be able to write this as x minus 1 times 4x to the 2nd plus 4x plus 6 equal to 0. And this is going to be the only real 0. We wouldn't be able to factor the remaining polynomials, so there's going to be no real 0 in this case. So x is equal to 1. So we would be able to say that the distance is minimized. The closest point to 3, 0. Closest point to 3, 0 is x is 1. And if I plug x as 1, y also turns out to be 1. So the closest point to 3, 0 is 1, 1 on the parabola y equals x squared. That's all in this video. We saw several examples of optimization here.